Hydraulic models are instrumental tools for all the water utilities worldwide, and they are constantly used to drive all the major investment decisions. That's because every hydraulic model is essentially a cheap representation of a system which drives hundreds of millions of continuous investment. So a small investment on a model could easily translate in huge saving when operating or designing the network. So we build this mathematical representation of the real network. We make sure to compare modeling results with telemetry, essentially to validate the model outcome. And then we can use the model for a series of different purposes, including master planning, risk assessment, plant maintenance, and more. Today, we're going to focus on one specific use, which is network optimization. The assumption is that we can operate our pumping station at off-peak electricity to save money. And the objective is to find the near optimal pump schedule which satisfy some hydraulic criteria that we can define and at the same time minimize their operational cost. This is quite important, as if we were just to optimize the cost, provided that we have enough storage in the network, we could simply pump overnight and feed the system by gravity during the day, which would impact in huge cost saving. But in this situation, however, we will probably end up with a very low level on the service reservoir, which, as we know, is supposed to absorb demand fluctuation and as well as provide storage of water in case of an incident. As such, the cost saving that we might have achieved in the pump schedule might not be enough to justify the risk that we have to take by having an empty reservoir. So the balance between cost saving and the acceptable level of risk must be considered in the definition of the near optimal pump schedule. And this is where an hydraulic model can be used to simulate different operational control and evaluate side by side associated cost and risk. The question is then, how many scenarios do we have to analyze? The complexity of this is clear even by looking at a very simple model, with 3 pumps feeding a service reservoir. Assuming that each pump is either on or off for the entire duration of the optimization period, and assuming that we are simply looking at fixed speed pump, we will have 8 possible combinations to analyze. This is not much, but it's clearly not good in order to optimize the system, as each pump can be turned on and off several times during the optimization period. And here is where the complexity starts. If we assume that each pump can be either on or off for half of the optimization period, we will end up with 64 possible combinations that we need to analyze, but that is still not ideal. We can continue, and assuming a single day of optimization period, should we want to be able to change the pump control each hour, we will end up with 5 times 10 to the power of 21 possible combinations that we need to analyze. And this number will further increase should we assume to change control on a 15 minutes interval. So this is a quite complex problem to solve, and the solution that Innovice have identified to address this specific problem is to generate a mass balance model from the hydraulic model. The mass balance is a simplification of the hydraulic model, which runs considerably faster. So the system can analyze cost and constraint using a genetic algorithm, which can be also run on a multi-thread to further improve performance. So that essentially means that we can run the optimization using the computational power of different machines that we can put together in order to increase the performance. The downside of using the mass balance model instead of the hydraulic model is the precision. So what we do then is to double check the result of the mass balance model by running a new hydraulic model with the pump schedule that has been identified from the mass balance model. And if the results are in agreement, then the near optimal pump schedule is provided to the end user. When we look at a real case example, this is a real model with a real electricity tariff. We can set the hydraulic constraint that define, as we saw before, the acceptable level of risk that we're willing to take. So we can set constraint for the reservoir, for example, minimum, maximum level of percentage full during the optimization. the depth that we want to target at the end of the optimization period. But we can set constraints on the pump as well. So number of switches, cost of switches, that is quite important, as if we want to reduce the maintenance cost, we need to reduce the number of switches because there is a direct connection between the two. So that's an important factor that we need to consider in the optimization as well. So when we look at the result, by looking at a graph with the level on the reservoir before and after the optimization, it's quite important to observe that we are starting and finishing at the same point. And that is essential in order to make sure that we are comparing the two different configurations on a like-for-like basis. If we then look at the cumulative cost for the two pumps that we are trying to optimize, you can see that after the optimization, we managed to gain a 7 to 8% saving, which is a lot considering the electricity cost that the water utility normally pay on a yearly basis to operate the network. This is therefore a good achievement, but there is a further level of optimization that can be achieved. So if we look at the degree of insight with the action that can be taken based on the information that we have, as we saw, the model can define global rules to achieve cost saving. But within a real network, we have different operating conditions, starting from changing in demand, valve operation, pumps that might not be working or temporary offline for maintenance. So the optimization of the system using a static model is only good as we want to describe global rules. Our final goal should be to deploy an optimizer which is capable of prescribing control based on the real condition on the network. So the first step for achieving that is to move from static to dynamic modeling technique. And this is clearly where the industry has been going over the past few years. Here is where we start differentiating between offline and real-time model. A real-time model is the same as the offline model, but is constantly updated to account for change occurring in the network, like asset failure, reservoir level, and valve operation. Line models also account for change in the demand, leveraging on demand forecast performed at a DMA level. So with this capability, we have essentially a system, a live system, which runs 24/7. And this system is capable of supporting operation to make better decisions. So for example, in case of an incident, we have the forecast of the model that is constantly compared with the telemetry. The incident might cause a pressure drop. So by continuously comparing these two values, and we can create alerts on deviation that highlight the problem to the water supply operator. The model can then be used to understand the impact of the incident, define how the incident is going to evolve, and support with the definition of the best operational response. So this is better efficiency, better decision, and this is also relevant when we talk about network optimization. But based on the forecast, we can actually run the optimizer as we saw before and basically use the mass balance model with the genetic algorithm running on a multi-thread optimization engine so that we can get the response for the best way of operating the system based on the actual condition of the network. At this point, when we move from planning to operational mode, time is the key. When we are on a planning mode, we can afford to wait 2 days for the optimization to complete because we are just defining global rules. But when we are on operational mode, we want to get the result as soon as possible. So time is the key. That essentially means that we don't want to start the optimization at midnight, getting the result at 8 a.m. and the results are telling us that we should have operated our pump between 1 and 5 a.m. because that would be too late. So time is really important. When we look at our case study with a real network with 49 pumps and 18 reservoirs, this combination of mass balance, genetic algorithm, and multi-thread simulation basically managed to complete the optimization within 5 to 9 minutes, which we think that is good enough to support operation with the definition of the best operational strategy, considering based on the network condition.